Okay, welcome to Tabular Integration. So this is a method that we are going to use to avoid repeated use of integration by parts. So recall in your notes on integration by parts, we used this same example right here, and we had to use integration by parts 2 times. It's pretty tedious, it's pretty messy, there's a lot of writing, it's easy to lose a term somewhere. So it's rather complicated if you have to do integration by parts more than one time. Integration by parts is ideal if you just have to use it one time. Okay, if you're one and done, it's a piece of cake. But if you have to do it more than once, then you want to use this technique called tabular integration. So when do we use this technique? Well, first of all, it's when we are integrating a product of two different functions, which we're calling f and g. Now the first function, which we're calling f of x, all right, this function here can be differentiated repeatedly to become 0. So if you have something like x squared, we know its derivative is 2x. The derivative of that would become just 2, and then after that it would become 0. So if that leading function, f of x, will eventually go to 0 after you repeatedly take derivatives, then that's the first requirement. And then the second requirement is that this g of x dx, all right, or think of it as what we called dv before, that can be integrated repeatedly without difficulty. All right, so let's see this in action here. So the first step is we're going to make a little table. Okay, think of tabular integration as integration where we're using a table. Okay, so on one side we have f of x and its derivatives. So we are going to use this x squared as our f of x. And then on the other side we have g of x and its derivatives. Okay, or I'm sorry, its integrals. So let's start with the f of x and its derivatives. So you're going to simply start by just writing down x squared, and then you're going to write its derivatives underneath until you hit 0. And then on the other side you're going to start with g of x, which is e to the x, and then you're going to integrate. Well, this is e for easy, okay? And I'm going to stop when it lines up with the 0. Okay, so from here we are going to draw these diagonal lines connecting these terms, and these are going to be products. Okay, we're going to be multiplying those together. And we are also going to be using these signs, plus, minus, plus. It's always going to follow that pattern, okay, starting with positive. So if we, I just draw an arrow here, if we are looking to integrate that, our final answer is going to be, well, we have x squared times this e to the x, and it's supposed to be positive according to that. So we're just going to have x squared e to the x. Okay. Our next term is going to be minus, okay, or negative, and then we have our product of 2x e to the x. And then finally we have a plus because of that right here, and then we have 2 times e to the x. And then a plus c, don't forget. So this is the same answer we got when we did integration by parts repeatedly. All right, and again, this is a heck of a lot easier. All right, integration by parts is only ideal if you only have to do it one time. Okay, if you have to do it more than one time and you have the situation where eventually you will get 0 down here for your derivative, then you want to use this technique of tabular integration. Okay, let's do one more example. So again, if we were to try to attack this using integration by parts, it would take a very long time. If we look at this and break it up into 2 parts here, we see we have an x to the third, and if we were to take a whole bunch of derivatives, we would eventually get to 0. So this is ideal for tabular integration. So let's make our table. Okay, so let's first start with f of x and its derivatives. So we have x cubed, which then becomes 3x squared, which then becomes 6x, followed by 6, and then 0. Over on this side we have sine of x, When we integrate that, we get negative cosine of x. Now when I integrate just regular cosine, I'm going to get just positive sine, but then that negative in front will come along, right? When we integrate cosine, we get sine, so negative cosine becomes negative sine. Well, from there, if I were to integrate just positive sine, I'd get a negative cosine, but that negative in front would turn into a positive, okay? And then from there, I'd be back to sine of x, and then you can see the pattern here developing. All right, but we would stop because we're now at the row where we see 0 for the derivative. So this is where we're going to now connect diagonally, okay? And then from there, we alternate our signs, starting with plus. This really is incredibly easy. So you're now going to just multiply these pairings together. Okay, so let's do that. So we're going to have x cubed times this negative cosine of x. It's supposed to be positive, however there is a negative in front of that cosine, so we would have a negative x cubed cosine of x. My next term here, I have this negative times this negative, which will turn into a positive 3x squared sine of x. And then I would have a positive, right? And then 6x, so plus 6x times the cosine of x. And then finally we would have a, go down here, minus 6 sine of x plus c. So you're literally just connecting these products and then just throwing this sign in front. Don't forget that there could be another negative in here. Okay, so that's it, guys. That's tabular integration. There really isn't much to it, but the requirement is you have to be able to get down to 0 for your derivatives, and this needs to be fairly easy to do, all right, for this to be a candidate for what we call tabular integration. Okay, bye-bye.